Okay, so today we'll be proving the Pythagorean theorem 3 different ways, but in increasing level of difficulty. First, what is the Pythagorean theorem? Well, it's a theorem that states that for a right-angled triangle, like this one, of sides A, B, and C being the longest side, also called the hypotenuse, we have the identity a squared plus b squared equals c squared. Now, I'm sure you've all wondered where the heck does this formula comes from. So we'll be coming up with 3 different proofs today with as little math as possible. Okay, proof number 1. This is the easy one. Here's the setup. We have our original triangles with sides A, B, and C. What we're going to do is add more triangles and arrange it so that the A side is on top of the B side. So we have A and B here and a right angle between the C sides. We're going to repeat this process 3 times like that. Notice that these triangles form an outer square, but more importantly, an inner squared void of side C. So the area of that void will be c squared. Now, what happens when we move that void around? If we move this triangle up here and these two this way, the inner void now splits into 2 squares of areas b squared and a squared. Since it's the same void, but just rearranged differently, we can conclude that a squared plus b squared equals c squared. Easy enough? Now let's move on to a slightly harder proof. This is our setup. We have our triangle of sides A, B, and C. What we're going to do this time is redraw the same triangle such that the A side of our new triangle coincides with the B side of our old one. Of course, since A and B are different lengths, there's going to be a bit of a gap here. So we're going to repeat that 2 more times. Now, note that we get an outer square as well here, and since the side is C, the area will be c squared. Now let's try to compute that area a different way. Well, that area is also the sum of the areas of the 4 triangles and the inner square. The area of each triangle is a times b divided by 2. So we multiply that by 4 and we get 2ab. What about this inner square here? Well, its side will be b minus a, so the area will be b minus a squared. I'll spare you the math here and expand it to b squared minus 2ab plus a squared. So the total area will be 2ab plus b squared minus 2ab plus a squared. And since the 2ab's cancel each other, we get a squared plus b squared. So we've computed the same area 2 different ways. On one hand, we got a squared plus b squared. On the other hand, we got this c squared right here. So they are equal and we are done. Now, onto the third proof. It's going to be on the harder side because it uses the concept of similar triangles. First, what does it mean to be similar? Well, suppose we have a rescue dog here. A dog gives birth to a smaller dog, and for some reason, we decide to clone it and rotate it. We say that all these dogs are similar if their proportions are the same. So if we label the dog heights big H, H1 and H2, and the widths W, W1 and W2, we'll say that they are similar if the ratios H over W, H1 over W1, and H2 over W2 are all the same. What about similar triangles? Suppose we have a triangle here, and we decide to shrink it by hand to get a smaller triangle, then rotate it to get another one. As we've seen with the dogs, all these triangles are similar. But what's interesting with triangles is that the angles are also the same. So we can actually say that when 2 triangles have the same angles, they are similar, because we can always find a way to go from one triangle to the other, whether it's shrinking or rotating. So we save this fact and use it in our proof. Now onto the proof. This is our setup. We have a right triangle of sides A, B, and C. We're going to draw a line from the right angle of our triangle to the C side, forming a right angle as we touch the C side. Let's call the length of that side H. That line splits C into 2 smaller lengths. Let's call them C1 and C2. Now let's consider this inner triangle here. Its sides are A, C1, and H. And it's also a right angle triangle. Now notice that this small triangle shares an angle with our bigger triangle here. Since it also has a right angle, the third angle will be the same as well. So these two triangles are similar according to our fact from before. It's kind of hard to see that from here, so let's flip this triangle. There we go. A gets here, H gets here, and C1 gets here. And we have our same angle as before up here. I encourage you to stop this video to try to understand how this rotation happened. Now we can see that these two triangles have the same proportions, so we can say that A over C on the bigger triangle equals C1 over A on the smaller triangle. If you rearrange this equation by cross-multiplying, we get A squared equals C times C1. Let's save this for later. We do the same thing with the other small triangle. We draw it over here, the sides are B, H, and C2. Again, these two triangles are similar, and to visualize it, we're going to redraw the small triangle such that the H side is standing up like this. We get C2 from here and then B here. Now we can write the proportions B over C on the big triangle equals C2 over B on the small triangle. We cross multiply again and we get B squared equals C times C2. Now we take our two equations and we add them together. We get A squared plus B squared equals C times C1 plus C times C2. We factor out the C on the right side and get C times C1 plus C2. But remember, C1 plus C2 equals C. Now take a break here and dance a little bit if you understand how beautiful that is. So we get C times C on the right side, which is C squared again, so we can conclude that A squared plus B squared equals C squared. That's it. It wasn't so bad, was it? Well, thanks for watching. If you enjoyed the video, don't forget to like and subscribe. That encourages me to do more visual proofs or other videos like this. And remember to also click the notification button as well. Thank you. Bye.